Many thanks for the kind introduction, Jay, and also for this invitation. I'm delighted to be here. And also, I would like to thank all the attendees, including my two students, Olivia Daust, Olivia Belanger, and in addition, Jorge. Thanks for being here. So I am happy that there are some people that I already know, and I'm looking forward to meeting the rest of the attendance. So thank you for being here. And as Jay, you mentioned, I try to be rather active in this field of mega-constellations. I am chairing the special interest group that is connected with the satellite and space communication focus group of IEEE. In addition to that, we are currently preparing a best readings collection. So it's a rather active field, and it is the interest to this is increasing day by day, and it's a very I have been working in communications for, as you mentioned, I don't want to count the years, but it's over maybe 2 decades now. And the field that I worked was never so much in the news. I have never seen so much things about it in the news. And I'll try to wrap up my talk with the spy balloons, actually. So I think it's like a very active field, and it's, every day there is something new happening. And yeah, if you have any questions at any time, please feel free to ask them. So yeah, so this is my title slide. I will talk about communications and networking in LEO Mega-Constellations. The difference here is the mega word, because before that, LEO constellations were also already available. But there is a tendency that from the business perspective, they are not sufficiently profitable. So that's what we have been seeing with Iridium. So hopefully it will be different this time. To proceed a little bit about facts from Polytechnique Montreal, is like so we are a university based in, we are a Polytechnique university, which means we are only engineering university based in Montreal, and we have excellent views. We are located at the mountain in Montreal, if you have ever visited it. It's about 9,500 students, and it's the number is increasing with 28% women. And the university dates back to 1,873. So we are celebrating the 150th anniversary these days. We are happy about it. And it's a research-oriented university with a significant institutional research budget. So just 1 second. Okay, so so that's where we are based. So if you ever want to visit Montreal, send me an email, and I'll be happy to communicate with you. The talk today, I will first start with the emerging mega constellations. They are all over the news, of course. The SpaceX is there. Project Kuiper's plans are being discussed by FCC. So I'll start with that discussion, and then I will continue with the standardization aspects, which I hope will be the main difference that will make it viable from the business perspective. From the technology perspective, it's already up there. Then I will try to give some information about the research that I have been conducting so far with my colleagues, with a focus on the communications in space. So satellite communications is a rather, say, classical field. It created the origins for the many communication standards either. But there will be some new let's say development. So I'll try to focus on that. Especially, I will focus on two different communication systems, one like not the systems but the architectures, space to ground and space to space in terms of the inter-satellite communications. The novelty here, which didn't exist before, will be the networking aspect. So the networking aspect is rather new in space, and I'll try to say a couple of words about that part as well. It is a emerging area, I must say. Then I will talk about future research directions, including a little bit of the security aspects. And in terms of the security, that is where I'll try to speculate about these spy balloons, which is basically a paradigm that we have been playing around with since 2021. And yeah, it's connecting satellites with the ground will surely benefit from these stratospheric devices, I should say, instead of balloons. So I'll talk about that and finally conclude my talk. Okay, so first, starting with this sustainable development goals of the United Nations. There are 17 goals defined that is targeted to be achieved by 2030. And these goals are are designed with the hope of improving the quality of life for everyone living on this planet. And this includes varying goals, of course, including the elimination of poverty, elimination of hunger, and all these. But if you look underneath these goals, most of them include global internet access as an essential enabler, like quality education. This is something that we have seen during the COVID times, where almost all education had to be transferred to online systems. So having internet access is basically rather important and a necessary condition to be able to reach these sustainable development goals. Now, associated with goals is the paradigm of leaving no one behind. And during the pandemic, we have seen that the humanity is ever more reliant on internet connectivity. Here, I would like to read a quote from a report of the UN Secretary General's high-level panel on digital cooperation. And the quote of Mr. Gates and J. Ma indicates that access is a necessary but insufficient step forward. To capture the power of digital technologies, we need to cooperate on broader ecosystems that need to enable digital technologies to be used in an inclusive manner. So this cooperation is basically the main paradigm that I would like to focus on towards throughout this talk. And when we are again talking about this internet connectivity, we are not only talking about urban city centers. There are also so many rural centers where the internet connectivity can only be provided by satellites. And I have included a map that shows the satellite-dependent communities in Canada, especially in the Northern Territories. The satellite connections is an essential aspect of daily life. So when we look at the satellite networks, things are changing very fast in this domain with very ambitious plans. There are many countries, and then in each country, not only on the national level, but not only from the government's perspective, but also private companies that have been launching a number of satellites. And there's a big, there are ambitious plans for the future. With Starlink, Starlink is the leading player in this domain with the plans of 42,000 LEO constellations and the deployment. OneWeb is aiming about 6,000 satellites. Amazon Kuiper is aiming about 3,000 satellites, and Canada's Telesat is also aiming to construct a network in the future for about 1,600 satellites. And of course, these plans change daily, and these numbers are updated daily. But it is clear that this space is getting more and more populated. So the table that I have placed on the right side is from a very recent paper that got published in February, that's based in Transactions and Communications. And there we have included these numbers, but by the time in about a year, these numbers will change. So that's what I'm trying to say is this is a very dynamic area, and almost every day we can see a related development. And here I collected a couple of news bullets from last September, and of course I can extend the samples, but a couple of things that I would like to emphasize. First of all, there are new players coming into the picture. There are new developments in terms of the cooperations between the companies that we are seeing. So from all these perspectives, it's a rather dynamic field, not only from a company-wise, but the dynamics between companies are also changing rather quickly. So the news bullet from the left side indicates the cooperation between Apple and Globalstar, where SMS messages or short messages can be sent through satellites in case of urgencies. In the middle, we see an example of the 5G deployment with OneWeb satellite. So this is a trial of the 5G network with the existing satellite constellation of OneWeb. On the right side, we see an example where you can connect to internet on a cruise ship using the onboard modems of this ship. So there are all these developments, and we keep seeing additional examples. And these developments are also getting very, I say, adventurous and ambitious. Another example that I have is this AST Space Mobile's Blue Walker 3, which is a satellite that aims to connect directly to the cell phones. So just to give you the difference between those two paradigms and show you the shift between the paradigm. I'm not sure if you can see the cursor, but here we have special terminals that needs to increase the gain to be able to connect to satellites directly. But looking at the another type of solution with AST Space Mobile's satellite, we are looking at a giant antenna array. By giant, I mean about 700 square foot communication antenna, and with this many antenna elements, what we are doing is we can basically increase the gain, and then we can eliminate the requirement of specialized terminals. So we can directly connect to the satellite using our phones. So this is more like the integration paradigm that is targeted by the United Nations. So we are getting closer there. This is the good part of the news. And of course, there's always advantages and disadvantages. And I was asked this question by Heinz Geller in one of the weekly Technology Society lectures that I was given. And coming to the disadvantages, okay, what are the problems associated with them? The radio astronomy is very much impacted by the pollution, light pollution that is created by these satellites. And companies are trying to find solutions. Here's one example, which is dubbed as DarkSat, to be able to limit the reflection from the satellites to not to disrupt the observations by the radio astronomers. Another issue is that of the space debris. There are so many bullets like that. With this title, I will read the title. Space debris expert is saying that the orbits will be lost and people will die later in this decade, and it is rather scary from looking at this. In a multidimensional way. So we have to have a harmonized way of development of or a sustainable development of space. And this is basically this has to be accompanied with the tractable space debris, which is basically an issue that will pop up in the news in the future. And finally, coming back to the AST space mobile solution, this is what, let's say, an interpretation of what could be expected. We actually don't know about it, but there are these, I would say, there are predictions. And with this giant antenna array, the problems can become even more critical, both from the radio observatories or radio observations, radio astronomy observations, and also from the space debris perspectives if a collision happens. So it's like it's a very critical subject that needs to be handled in a multinational manner. So what has been happening is, as I try to emphasize, there are all these developments with satellite constellations on with different companies. And so far, from the economical side, it still doesn't actually make a lot of sense. And there are all these discussions about how to make these constellations profitable. So for serving the underserved or unconnected communities actually doesn't actually introduce a viable business unless it's subsidized by governments. And so far this wasn't a success, but I am rather optimistic this time, and I will try to justify this by looking into these standardization aspects. So what is happening from the research perspective? I have been working on 6G, so-called 6G research for a number of years now. And there are all these different say features that is included within the paradigm of the 6G evolution, that varies from the use of sub-terahertz and terahertz bands to reflective intelligent surfaces. But I will try to look at the difference from an architectural perspective. And in this architectural perspective, we are actually looking at a vertical network, which will be composed of a terrestrial network, which is basically the current network that we already have. And in addition to that, we will have an aerial network, which we are also seeing some deployments about it, including some UAVs and drones, which could be used as both as a user equipment and a base station. So, for example, drone-based delivery systems would rely on the aerial network. And I would like to introduce another component that wasn't known before, not as much. It wasn't in the news, let me say, which is the high altitude platform station. And high altitude platform station is like a stratospheric station that is located between around 17 to 25 kilometers from the surface of the Earth. And it could be all these balloons that we keep hearing about. And then finally, the third layer is the satellite network that contains the combination of low Earth orbit, medium Earth orbit, and geosynchronous Earth orbit satellites. So all these three layers are envisioned. So how can we combine these layers? That is the main problem that researchers are trying to address. Each layer comes with its own set of advantages and disadvantages. And space layer, the satellite layer, comes with its own advantages that has, for example, because of the multi-layer structure, in addition to geosatellites, the LEO satellites are introducing some favorable link budget and high SNR conditions. In addition, satellites have rather large footprints that provides a good coverage advantage. Regarding the challenges, the high mobility of the LEO satellites with the very fast motions around the Earth is a problem. Latency associated with the round trip delays is a problem. And of course, it's prone to some attacks, which may also be an issue, security attacks. The aerial network, on the other hand, is composed of both lower altitude platforms like UAVs and high altitude platforms. They have their own advantages, like with the flexible deployment, cost-effective wireless services, much lower round-trip delays, and low path loss. And of course, whenever there's an advantage and there's a disadvantage, so the challenges are the high mobility and sometimes the lack of coverage, especially with the UAVs, because we don't have vertical coverage on the ground. So how will we make sure that they work with one another is the only solution that is available for a harmonious deployment is standardization. So when we have this standard, then there will be multiple companies following this standard, and there will not be a compatibility issue. I must say that the current satellite deployments, most of the information about the communication systems is proprietary, so we don't actually have a lot of details about the design of the communication systems, and there is no standardization that is enforced in this domain, especially with the free space optical communication. So the key to success, as I see it, is mainly standardization. So of course, standardization groups are also aware of this, especially 3GPP, Third Generation Partnership Project, is very active in this field. And here's an overview of what is happening from the 3GPP perspective, especially on the left side. Even starting from release 15 and 16, in the product level, we start seeing about the use of satellites, and and other aerial network components in the networks. Of course, their role is expected to increase when we evolve towards release 2022. And they will also include smarter satellites. Of course, I also need to mention that 3GPP is not the only standardization body that is promoting these. There are the ITU is also the International Telecommunication Union is very active. ETSI is very active. There are some national initiatives as well, and satellite standardizations like DVB group of standards are also progressing rather well. And by the time they are evolving towards 6G, there will be more features that needs to be included. But so far, we can say that the standardization groups are taking this issue very seriously. And what is happening is basically from the standardization, especially in the 5G generation deployments, 3 different dimensions are highlighted. These include the service continuity, so that we will have continuous services. We will have service ubiquity, so that we will be able to access services regardless of the constraints and the location. And finally, service scalability, when we are talking about the increased number of users, because of the software based nature of the network management structure, we will be able to accommodate our offer scalable services. So these are the planned use cases for the 5th generation. And as I mentioned, even starting with release 15, the non-terrestrial networking elements, NTN elements, are already in the picture. And of course, there are so many other things that needs to be developed following this. But just to give you an idea, I have this table from one of the technical recommendations of 3GPP. So this is from 3GPP TR 38.821. And here we can see 3 different satellites that can be used at the base station, LEO, MEO, GEO satellites, and then unmanned aerial system platforms, including a high altitude platform station. And also we can include high elliptical orbit satellites with varying altitude range. So each of these devices have different footprints, and they are actually rather large, including the footprint of the high altitude platform station that can go up to 200 kilometers. So this is basically something that can be deployed already, even in the standard form. So it's not a distant future. This may actually be the key for the economical success of the satellites. But how will we integrate these? So integration is also a different story. That changes with respect to the capabilities that we would like to include in the satellite, and there are different deployment or integration scenarios in this slide that is based on the technical recommendation 38.821. And here in the first one, we can basically see that the satellite is working as a conventional radio frequency band pipe and sending this, so it's just simply working as a forwarding relay, and the signal is collected at the remote radio unit, which is the base station GNB. In another deployment, we can actually do some of the processing. So we can actually shift some of the functionalities of the base station to the satellite, and then leave the rest on the network that is connected with the remote radio unit, and the interface between the two components can be defined over the satellite connection. So we can also shift the whole GNB's functionality to the satellite, and then make the rest of the core network connection with the radio unit, again with the satellite to ground network. What we can do is we can also use this satellite as the conventional band pipe with the first strategy. However, we can try to connect jointly to the satellite and the base station. We can extend this scenario to connect one user equipment to two satellites, and which are already also in band pipe scenario, which that means most of the processing is on the outside the remote radio unit. Or finally, we can try to put two base stations up in the satellites and connected to the remote radio unit. So these are all different scenarios that can be extended. And especially with multi-connectivity, that also provides a way of increasing the signal-to-noise ratio, and provides an advantage or provides an option to have connections directly with the user equipment. Another, perhaps I need to also mention that here, in addition to the conventional user equipment, we still see a satellite dish. The goal, the ultimate goal in the Holy Grail here is directly connect with the user equipment and not use a specialized satellite dish. So this is basically the evolution strategy of the integration of the terrestrial networks with the satellites. In a bit further in the picture, our vision in this paper that we have written with Professor Teslim Dervish, these networks will need to be evolving in an autonomous manner. So once we have two satellite connections, we can easily extend it to multi-satellite connections, and then we can easily extend it to multi-high altitude platform connections and perhaps a drone swarm. As the systems get more and more complicated, at this time we can start talking about the machine learning paradigms and how the network will be optimizing the radio resource management functionalities to be able to address the strict requirements. So this is basically the evolution of the network, which we adopt as the self-evolving network. And this may be one of the ways that all these vertical architectures can function in a harmonious manner. And of course, we are not only talking about single band, we are talking about multiple bands, we are talking about free space optical communications, and wherever possible, fiber optic communications for the backhaul connections. So this is what is happening from the standardization aspects. And I would like to continue with the communications, the developments in the communication perspective. And I'll focus on the first space-ground connectivity. Now, for space-ground connectivity with satellites, or maybe with high-altitude platform stations as well, we can talk about two different solutions. One of them is the radio frequency communications. And these, with RF communications, the advantages are clear. the weather has a negligible effect. I mean, it has an effect, but it's negligible compared to the other solution, which will be the free space optical communications. In the absence of line of sight, we can still make the system function in it works in non-line of sight regions. It can be used for various different applications with satellites, of course, radios, broadcast, and medical systems. Regarding the challenges, we are talking about the congested spectrum, especially for terrestrial networks. So we have to make sure that we are working with in an interference controlled environment. The data rates may be on the lower side. There is problems associated with the fading, multipath fading, the shadowing aspect. There is molecular absorption and rain attenuation. And finally, there are security risks, meaning that with the large footprints, we are subject to eavesdropping attacks, and also because of the wireless nature, we are subject to man in the middle and spoofing attacks. But this RF communication is a well-established solution, and especially with the high throughput satellites where we have multiple beams, as you can see on the right side of the picture, we can achieve high data rates. From high data rates, it is that is the very subjective metric. The best case satellite scenario so far that is envisioned by SpaceX in their cooperation with the operators is about 4 megabit per second. So it's still much lower than the Wi-Fi speeds. But in the absence of connection, that is really advantageous, especially given that with current technology, we are only talking about very low SMS services, text services. So looking at the solution from the second approach that we can take is for the space ground connectivity is to use free space optical communications. Now, in these kinds of systems, we use lasers or light to transfer information. It is once it's finely calibrated, extremely high data rates can be obtained. It is license-free. Licensing in RF bands is a very a detailed process and very expensive process. So license-free systems such as the free space optical communication systems are rather attractive. They are very difficult to intercept because we are looking at a very, very narrow beam. And the transmit power requirements are lower than those of RF. However, in the presence of any kind of fog, cloudy weather, snow or dust, the propagation conditions deteriorate very rapidly. If there is atmospheric turbulence, we may not be able to align the transmitter and receiver properly. The atmospheric attenuation is still an issue, and the pointing problems can also reduce the signal-to-noise ratio. However, there are a number of examples that show that this is technically feasible. So in our research, we were trying to look at these two different aspects, RF and FSO, especially in terms of the system models, the mathematical models, we have shown that there are some solutions to overcome these challenges. The first solution that I'll talk about is to use RF and FSO in a complementary manner. Then I will talk about cooperative communication scenarios. I will then discuss a little bit on the MIMO extensions, multi-antenna, multi-input, multi-output extensions. And here we are actually looking at cell-free constructs. The reason that we are looking at cell-free constructs is simply because when we are thinking about LEO satellites, there is no well-defined cell because they are also moving very rapidly. And finally, we are trying to understand if we can use these metasurfaces, instantly configurable metasurfaces, which are referred to as reflective intelligent surfaces, to improve the signal-to-noise ratio. So the first solution that I will look at is this the use of RF and FSO in a hybrid manner, and this is from a recent paper that is authored by Olfa and my colleagues Professor Erdoğan, Professor Altunbaş, and Professor Yanık Ömeroğlu. And in this very simple construct, we try to use RF and FSO in an adaptive manner. So if we have context-aware sensors and in a satellite, then the satellite can select the advantageous transmission strategy. So it's actually a very simple idea. What we try to understand is, like, there may be, we try to look if there may be any scenarios where dual use would make sense. And we have seen that, especially for in thin cloud, it would be better to use both of them at the same time to improve diversity. And I don't want to go into details of the simulation results, but we have seen that this kind of solution, the hybrid use of RF and FSO links, is actually rather advantageous. Of course, I'm just talking about the communication perspective. If we want to look at the disadvantages, the payload size will increase, and it should be also analyzed if it would make sense economically to send both kinds of payloads on a satellite. Another kind of solution we looked at is the site diversity on the ground. We try to look at it in an upside down manner as well, where we want to connect an Earth station with multiple satellites. And in this kind of site diversity, of course, we can just connect every other ground station with fiber optic. It provides a significantly higher performance. However, it's of course very high cost, and we also need to worry about synchronization, although it's much more easier of a problem when we are looking at the downlink for the if we consider multiple satellites, then synchronization becomes a bigger problem, especially because of the mobility between these satellites. So when we looked at this kind of a diversity, if we increase the ground stations, the communication gain is rather easy to observe, and we try to note these in this paper, in this IEEE Access paper. Then we try again with Olfa and ALAM. We started investigating whether it would be useful to use these stratospheric balloons, like high altitude platform stations. And these high altitude platform stations are actually an incredible solution to collect the information from the ground and then send it to the satellites. In this construct, we try to use RF connection between the ground station and the high altitude platform station, and the HAPS platform uses free space optical communication to send the data to the satellite. And if the satellite cannot send it back to Earth, there may be another high altitude platform station somewhere around the world to be able to send this data. And we try to understand how this kind of a construct would improve performance. And we have seen a significant advantage in terms of the signal to noise ratio. And then once we solve this advantage, I don't have the details here in terms of this outage probability and the bit error rate. We then extended the construct to multiple high altitude platform stations. And of course, with this kind of a construct, we have seen a significant amount of performance gain, as you can see from the changing slope in this outage probability curve. So these high altitude platform stations are actually super advantageous when we want to connect the ground stations with the satellites. And then from the satellites, of course, they can serve as a backhaul to be able to collect all this data. And this is from a recent paper. Again, first author is Alpha. And this was the paper after that Alpha received her PhD thesis, so defended her PhD thesis. So I'm very happy with all her work. The extension of this paradigm is we started to look at the problem from the upside down perspective, as I tried to hint a little bit a while ago. And in this kind of a structure, we try to connect the user equipment directly with the satellites. This is also seems like very advantageous to be able to connect phones directly to the satellites. However, from the design aspects, it's rather complicated. We have to it needs to be finely optimized, not only from the duplexing and pilot assignment perspective, but the beamforming, handover management, and synchronization perspectives is a big. It may be a big headache. And finally, we try to extend this this kind of a construct by including multiple clusters and then defining communications between these clusters. And of course, again, on paper, it's looking rather promising. So we have applied for a patent on this solution. Another solution that I would like to, another kind of, let's say, novelty in this field could be the use of metasurfaces. And for that, we are trying to investigate if it makes sense to include some metasurface coated solar panels on satellites, and based on the mathematical models again, we obtained rather advantageous results, especially for IoT scenarios, Internet of Things scenarios. And we also try to see this, see if we can make beamforming, and we can include broadcasting services with this kind of a scenario. And again, this looks advantageous. Of course, this is a multidisciplinary domain, so communications models are just one part of it. That's why I'm trying to be cautious when I'm explaining the numerical advantages. So there is more aspects that needs to be considered for these. And finally, within this kind of constructs, of course, with the machine learning and the benefits of machine learning is there, especially with say geometry based channel models. And currently, we are in the process of looking at these kinds of constructs by looking at the, and we are focusing on graph attention networks. So this is a work that is still ongoing by Kürşat Tekbik. So we are still investigating this paradigm. So that was the space to ground connectivity. And Jay, I'm trying to be cautious of the time as well, but let me know if I'm too slow or something. So I will.
You're doing great.
Okay, thank you. So I'll try to look at the inter-satellite communication. So this part, this is where we are a bit more adventurous than the space-to-ground connectivity. First of all, we are, hubs pop up from every aspect of my research, as you can see. And all the hubs that I have been considering, they're all very innocent, so I don't want to pose any speculation. From the mathematical perspective, again, what we have shown that is if there is a high altitude platform station like a balloon, we can also use this to be able to control multiple satellites. So when we are looking at this mega constellation, the control signals and everything to be able to that we need for network management, they can be generated with from this high altitude platform station. And we have tried to investigate different scheduling strategies and show that this is also promising. So cooperation, especially from like when we are considering satellites from 400 to, let's say, 750 kilometers from the surface of the Earth, instead of trying to connect them to a ground station on the surface of the Earth, we can use a high altitude platform station, and the lack of clouds and the relative stationarity of this high altitude platform station seems very promising, actually. Now, now that we are looking at line of sight propagation with no clouds or only in free space environments, we started investigating the array of sub-array structures, and with these multi-antenna arrays, we can obtain rather high gains, similar to the idea that is executed by AST Space Mobile. And this would provide us a mean to extend the frequencies to much higher carrier frequencies, such as the terahertz bands. And we have tried to understand if it would be if we can actually make use of these terahertz bands for the sensing applications. And in this paper, in this conference paper, we actually tried this and showed that even because of the structure let's say advantage provided by the array, because of the array gain, it is rather let's say promising to have to obtain a high localization accuracy, high angle of arrival estimation accuracy. And once we thought, okay, now that terahertz makes sense, may make sense in space to be able to use in larger with larger antennas, what other advantages can we exploit from there? So the solution to the second question turned out to be the use of joint communication and sensing system. And this integrated communication and sensing paradigm is very popular these days in the research community, and has a number of very promising applications. So we try to take this the use of because of the high frequency carriers that would that can give us improved sensing capability. We try to use this construct to be able to detect possible space debris. So this is like an automatic, like a bonus feature in addition to communications. And then with this feature, we can try to understand if there is a debris between the transmitter and the receiver. And the main the question that we try to answer is basically if there is is there like a multipath that is generated, and that is with this recent paper of Gizem that we presented in the Globecom in December, we tried to use chirp waveforms. The chirp waveforms are very high peak to average power ratio, and they are the ones that waveforms that is used for echolocation. And we tried to mimic this, and so that we can get actually very good accuracy to detect this. And finally, the use of intelligent surfaces is something that we have been playing around with, and we revisited the same paradigm in terms of the inter-satellite communications. And as long as we don't have a big, let's say, misalignment between the transmitter and receiver, we can obtain favorable results. So in terms of if we have if we cannot align them properly, then that's an issue. So so there are all these advantages and disadvantages. Now, finally, when I put all these things together, so far we have been talking about the communication on Earth for Earth, let's say, provided by satellites. We can also see that the satellites can also serve for the next step of humanity by extending the space networks to lunar communication systems, and then later for interplanetary communications. And personally, I believe that the use of additional stratospheric devices like high altitude platform systems, I mentioned them a lot, perhaps, but that is certainly advantages because of their stationary nature, and then aid with the Petlos exponents. So I will then, once I am convinced that there is this, it's possible to have space-to-ground connectivity and satellite-to-satellite connectivity. Now I will start discussing the networking paradigm, and this is this work we are doing with Dr. Pablo Madueri, jointly with my colleagues from Carleton, and then our colleagues from MDA and NRC, National Research of Canada. What we try to do is basically, now currently we are still playing around with the idea, but for our first solution, it focuses on the use of delay-tolerant networking. And this is basically, DTN is the current networking paradigm that serves us to collect data from space networks. So it's used in deep space communications and interplanetary networking, and it is designed with the conception that there can be high delay from at some length. So so it is say rather flexible, delay tolerant, it's rather flexible to possible delays. So what we try to do is we have been playing around with the idea of this bundle layer that is above the transport layer, and it employs a persistent storage on each DTN node to store, carry, and forward data packets as the opportunities are available. Opportunities are available not only from the geometric conditions between the nodes, but it also entails the traffic intensity. So based on this traffic intensity, we can make some advantageous decision. And because of the predictable nature of these the geometry between these devices, that the time varying let's say distances between satellites, we can devise a contact plan that is taking into account this connectivity. So far, this kind of an approach seems to be promising. So we are still working on ways to improve this performance. From the networking perspective, of course, not only the solution is not only with the routing, but also with the network management. And one of these in a work that we have conducted with, again, Dr. Teslim Darwish, we try to see how this evolution will take place, and that includes changes in the network slice management now that we have this vertical network, and the management and orchestration of the integrated satellite components, which have a very much time-varying topology, can be addressed with, again, with a little bit of forecasting for the, not only from the network topology perspective, but also with traffic demand perspective. And the management comes in a multifaceted problem. We will need to worry about management of satellite components, and then we need to also monitor satellites with split GMBs. So what I basically, in short, what I'm trying to say is, as we have seen that the satellite connectivity, satellite integration will come in multiple phases. As we progress more in these phases, we need to think about more details to be able to make sure that everything functions in a coherent and harmonious manner. And there will be some problems that haven't been observed before, like the location management. We are very much used to handovers on terrestrial networks. Handovers with satellites, with mobile nodes is something very different. The paradigm is rather different. Of course, we can use conventional approaches like anchor-based approaches that we have on the left side, but we may also have virtual anchors, or we may have cell-free constructs with that only depends on the connectivity matrices. So what I'm trying to say is some of the assumptions that we have been considering about the network deployments may not hold anymore. So we need to be careful about all these. So finally, what will happen in the future? First of all, one question that pops up: should we decide between RF and FSO, or should we make use of both of them in a hybrid manner? This is a question that we need to address soon. And I have taken this from a paper that we prepared for IEEE transactions on communications. I forgot to update this. It is actually published in the February issue, and it's about 70 pages long. So if you are ever interested in the future space networks, I can forward you the link. And then finally, the standardization directions is there's some work is already there. Most of the work needs to be done. I mentioned about the mobility management, but this also extends to other kinds of issues like spectrum management, fault-tolerant solutions, intelligent management and orchestration, the software-defined networking, and network function virtualization approaches, and finally the routing that we are still looking for a problem, solution for this problem. So the full integration needs more steps towards standardization. And finally, again, from the same paper, this is what we are thinking that will happen in the near future: deep vertical networks, where we have this interplanetary network between all these network clusters, SA elements. And this is one thing is different here than the mega constellation paradigm that I kept talking about. We may have satellites that are facing deep space, and then we will have satellites that are facing Earth, and then we may have multi-directional satellites as well, which we don't actually have at this point. And yeah, the mobility management is one of the problems that I'm thinking about a lot, and the unprecedented scenarios that that is basically yeah, we don't actually have a solution at the moment. It is a very good time to start looking into satellite research. And again, the spectrum management is something, along with standardization, global standardization. ITU is involving these the selection of the new frequency bands as agenda item in WRC. So this is also a very active field. And how will we be able to address these solutions? I think the answer is hidden in the cross-layer design. And the conventional design solutions that we have been using will be inadequate. So at some point we need to stop not exploiting the physical layer information in the higher layers. So we should have a combined design there. And finally, these are the slides that I just added today for this talk. What about the security? There are so many security problems, and I tried to look at some of them with Olfa in her research work. And we started looking at the eavesdropping scenarios most of the time. But here's one thing that we didn't actually look at all is the use of these high altitude platform stations as an attacker itself. So this is basically some of the results that I have from my previous work. Of course, so this is what we have seen. First of all, if we use a high-altitude platform station to collect information, we can significantly improve the secrecy level that is offered by this kind of a system. So this is good for if you want to send information from the eavesdropper that are down on the ground. This kind of a solution is certainly useful. Again, this is from a conference from 2021. Another construct that we looked at is the use of additional eavesdroppers along a high altitude platform station. So these are also prone to attacks like that. There may be other mobile devices around the high altitude platform station, and these high altitude platform stations may eavesdrop one another. And for those, we think like the connection between the satellite and the high altitude platform station. If it's like a free space optical, then it's more robust or more secure, I say. And finally, we looked at a problem where the a mobile device, let's say we adopt as a spacecraft eavesdropper around a satellite that can capture the data, and depending on the position, of course, we have shown that it is possible to do eavesdropping attacks. So those are all the security vulnerabilities that we may need to address in the future. So to conclude, with the integration of these networks, the 6G will leave, hopefully will leave no one behind. Everybody will be connected. And there will be new networking elements like high altitude platform stations and new frequency bands like terahertz that can help us with the communication problems. And we need to define the interactions of subnetworks. And to define these interactions, it's very likely that the machine learning approaches will become it will become like a useful solution. So I would like to thank all my collaborators, Halim Yanıkomeroğlu, Olfa, Teslim, Eylem, Pablo, Kürşat, Mohammed, and all other collaborators. And if you have any questions, I would be happy to answer them. Thank you.
Hi, Gunesh. That was wonderful. Thank you. Let's open it up to questions. Anybody have a question? If you're going to turn on your camera,
I have a question.
Go ahead.
I am Hisham al-Bakouri. My question is how you integrate terrestrial networks and satellite networks.
Very, very good question, Hisham. It's the integration is envisioned in multiple steps. In the first part of this integration, is just like the satellites are acting as relay nodes, but in the later stages, satellites are planned to be acting as like a base stations, almost like standalone base stations, and then we will also have according to the plans, we will have macro diversity, so that we'll have multiple base stations that are connecting to one user equipment on the ground.
So, sorry, what is the first step?
The first step is satellite is a relay solution station, just forwarding without doing any kind of decoding.
So it will forward traffic using some routing protocols like OSCBF?
Very good. Yeah, even that is not certain yet.
Okay.
Yeah.
Because I met Professor Mark Handley in SECOM, and it sounds like he's in UCL in England, and it seems like he's working on it, and he has some solutions, but none of them is like the ultimate one or the final one.
Yeah. So I must say that the current satellite networks that we have are very much separated from the terrestrial networks. So yeah, the 3GPP is preparing some steps in this multi-phase structure so that the integration will be possible.
Okay. Thank you very much.
Thank you.
Can you please put your email address in the chat?
Yes, of course.
Thank you.
George, you want to ask your question?
Yeah, I was wondering, I assume that at low Earth orbit, there's some drag from the thin atmosphere at that altitude. So my question is, how long are these low Earth orbit satellites expected to stay in orbit?
Yeah, very good question, George. I'm not an expert on this field, so I don't want to speculate. But all satellites come with their own lifespans, and that's a question that I'm also trying to understand how like once we deploy all these and their lifespans, and what will we do with it? And I'm not sure if this solution is there yet. There is this sensible space development philosophy, but it seems like the commercial companies are not actually following that. So, some of them are not.
Anand, you had a question in the chat. Would you like to ask your question?
Oh yeah, I think that was a pretty basic, straightforward question. I mean, we talked about this pretty large antenna in a satellite, 64 square meters. The idea is that you're trading off the antenna gain at the terminal to the antenna gain at the satellite. Is that the understanding?
Exactly. That is exactly what's happening in that model. But the issue is we don't know how many of these large antennas we can use in the orbit. And they, yeah, all of these, like, so far it's holding on well, depending on the news. Yeah, but there are so many unanswered questions. It's like a trial, and hopefully not an error. It's a trial for sure. Hopefully it will not end up.
Yeah, are these antennas phased array antennas? I mean, are they like, do they beamform and point to a specific terminal on the Earth?
I believe so.
Oh, okay, that's how it is. I had one other question on the free space optic link. You know, optics being what it is that likely to suffer more from attacks or interference, like interference from the sun? Because you can point another beam at it at a satellite to jam it relatively easily, rather than having to, in RF you'll have to spread that energy out, right? So I just wanted to know your thoughts on those.
I can give you a historical answer. In the I think in World War II, to be able to avoid interception, just light-based communication was used. So if we can align the transmitter and the receiver from security perspective, it's much better. But the question is whether we can align them properly or not, as you noted. So it's like if we cannot align them, then that's the big issue. RF, we are much better with RF.
Thank you.
Thank you.
Hey, George Amadeo, you had a question in the chat? Oh. Okay, let me see if I could find it again here. Okay, George asks, any comments about governance like spectrum allocation, orbital locations for HASP? Will it be a challenge?
Yes, excellent question, George. Thanks for this. The high altitude platform stations are actually, from the governance side, ITU has good, well-defined regulations for that, even from 1990. So it's like a paradigm that becomes popular once every 20 years, I guess. The issue is from the other than ITU, there is not much regulation, and that's basically probably what we are seeing in the news these days. Yeah, I'm not sure if it's, yeah, I don't have much more details myself either.
Does anybody else want to ask a question? So maybe I'll ask a couple here. So like, should I think of like creating a service or connection between 2 points on the ground, I guess, or well, let's say that, and would this be like an Ethernet protocol approach to creating services and links between customers? Do you have an orchestrator or something that's going to go through and build the connection, or does the protocols between the two with the IP address create the links through a lot of the satellites? It seems like a very complicated network to find your, it's a huge mesh network. It seems like it would be very complicated to find a path through the network, or the best path through the network.
Exactly. Especially in congested conditions, that will be a bit more problematic. So far I don't have a answer on how this is solved, because it seems like all the companies have their own proprietary solutions. But I can actually confirm your observations. It's rather complex nature, and so far, even with stationary routers, we are having some issues to be able to, let's say, address the scalability. Now that all the routers are moving in different directions and the routing tables need to be updated very rapidly. So it's yeah, things will get interesting for sure.
Oh yeah. So you're moving at 17,000 miles an hour, kilometers an hour.
27 kilometers, 27,000 kilometers per hour. Yep.
And so you're going past a lot of different other routers. You have to be able to communicate with that router. So you don't have much time to update your routing tables.
Exactly. So we are so far from the contact routing plan, we are trying to see if we can pre-store some of these to use. But of course, that also depends on the traffic intensity and the congestion levels. So it is not an easy problem as far as I can see.
So I mean, go ahead.
No, I mean, just chiming into that thought, isn't a lot of this known a priori? I mean, these orbits are kind of set, and errors, deviations from the a priori, if you can just address those, then knowing the location, you already know the table, and you only have to process the interrupts, so to speak, whatever is a surprise. Wouldn't that be the correct approach for you?
Very good point. Yes, that can certainly be exploited, but how frequent should we update the routing tables? And the relative positions of the satellites may change depending on the constellation selected. So if every node is moving in the same direction and we keep pretty much the same topology, it becomes relatively simpler. But for the other way around, if the relative distances are not kept the same, then it becomes like how frequent should we update it? How large of a routing table should we store? And then should we also consider the for example, if the satellites are moving just above a very populated urban city center, if it's too much traffic, should we also keep using the same routing table, or should we forward it to relatively less used satellites? Yeah. So there are a couple of details to be ironed out for sure.
Yeah, just a couple. Yeah.
I had a question, but I think you just answered it. The question really was, shouldn't we take advantage of the a priori information as to where these things are to establish the routing tables, not dynamically allocate them? But even in that scenario, as you point out, there's a high likelihood that something will fall apart in the information that we had.
Yeah. So that is the idea that we are playing around with Pablo, is to see these contact plans and then if we can make use of it. But even in simple simulations, there are so many. Additionally, the control information is rather heavy to be managed.
Well, thank you. I probably other questions, but thank you very much while I have a chance. Very complex subject and many new aspects to it. I'm an amateur radio operator, and just talking to satellite people are talking to satellites that we have is complicated.
Thank you for your comments.
Does anybody else have any questions? Aldo, do you have any questions?
Are you going to give us a presentation?
Yes, of course I can. Yeah, I can send it to Jay.
Okay,
Okay,
thank you.
that would be great.
Jay Chitra here. I just have one comment, not question, but amazing. It was amazing talk, but I don't fully understand a lot of it technically, but I did want to say, as a Red Cross volunteer, this is very exciting what she's talking about, that in the future for disasters, the communication could have a whole new arena to help get the communication working through the satellites directly from phones and things like that. So that's kind of my take on this one. This was very exciting to hear that.
But yeah, that is hopefully that will be the reality, and then it will be an really much of a much needed communication channel that will improve robustness of the networks, which failed miserably in the Turkish and Syrian earthquake.
Right, and then to hear all these news about people dying in remote parts of mountains and stuff, and to learn to see that iPhone 14, who knows, maybe in the future they can directly communicate and get help right away, so more lives can be saved. So that's very exciting. Thank you for this wonderful presentation. I don't understand any of the technical stuff, but just to see you, maybe I'll come to Montreal.
Oh, awesome. Thank you.
Très bien, très bien.
Merci beaucoup.
Hi, this is Aldo Cugnini. I do have a question. First, a very interesting talk, You mentioned the word simulation. I would imagine there are rather complex simulations that are needed to understand and plan these networks. Are the simulators essentially something built from the ground up, or are there any kind of commercial products that are available that come close to being able to simulate these kinds of networks?
There are some simulators that are looking at the part of these problems. So it's just like isolating a small problem and looking at it. And then I remember that I think last year, European Space Agency has some projects or call for proposals to construct their own simulator. So it's not available as of now, but I think it's under development, and we'll have it in about a year or so.
Probably a whole field in and of itself.
Yeah, exactly. It was just the call for proposals was just for the simulator, not for the algorithm, not for the technical solution, just the simulator.
Okay, thank you.
I have another question, not brought up by. Can I ask it?
Yes, go ahead.
How involved? How is terrain? This really brought up the emergency management thing. Really brought up a question. In Puerto Rico, we had a lot of geostationary satellites, really high, but they were low on the horizon, and you couldn't get to them because the mountainous areas stopped, direct paths. I would think that's a completely different problem in low altitude satellites where the actual visibility is going to be changing much more rapidly in that mode. Is terrain part of the equation in the analysis? That's my question, I guess.
Yeah, to be able to get realistic models, of course, you're right. The terrain and the elevation angle has an impact on the signal propagation, and there are these models. Especially ITU has a number of models that consider these. But in addition to the terrain, as you mentioned with the LEO satellites, the issue is like a LEO satellite is crossing the continental North America in about 7 minutes. So it's like things are moving rather fast. So for example, I can say that this call initiations, the authentication, the one by one, like authentication approaches, all of them will become problematic when we are considering fully integrated terrestrial networks. Of course, when I have a proprietary terminal, then they come up with these tracking algorithms and they are fine. But if we want to integrate multiple satellite constellations to one another, then we have to worry about all these in addition to the SNR conditions from terrain.
I muted myself, but thank you.
Thank you.
I'd like to ask another question, if I may.
Go ahead, George.
I came across an item where geosynchronous orbit satellites were being considered for this type of service. I wonder if you could compare, how that might, would that be advantageous, not advantageous, or, what's the thinking there?
The geosatellites, they have their own purposes exactly with the very large footprints, but the pad loss is so high about them, and also the round trip times make it very unsuitable to be used with other sort of services which require lower delays. However, I am envisioning that the geos have their own purpose to be able to, for example, if we can take some of the control plane information like the routing tables and all those things to the geosatellites, and they can coordinate the LEO satellites, that may be a harmonious way of working between them. But other than that, geos, they are good for non-real-time applications for certain, but for high data rate transmission scenarios, they are very difficult to work with.
Yeah, okay, that makes sense. Thank you.
Thanks.
One more question. This is probably a radio question more than a networking question, but in the space communication scenario, we're dealing with all kinds of strange velocities. So Doppler shift, is that an issue, or is that just something left to the radio to solve?
Very good question. So I think that is important, and I with one of my students, we came up with the idea in a paper that whether we can use this Doppler shift to be able to identify the spacecrafts from one another, because it's such a unique pattern. The issue is if it's predictable, that is excellent. If it's not predictable, then there's a huge if it's predictable, then it can be compensated. Otherwise, big problem, as you mentioned.
Thank you. That was good.
Yeah.
Just to follow up on that, is what about timing? I mean, you have objects at different altitudes are going to have different times. Does each thing need its own cesium clock in it?
That would be the ideal solution, unless we are talking about these CubeSats and extremely small satellites. When we are considering, for example, synchronization between these devices, that is also an issue, because relative distances between each of them is changing with time, and that all depends on their orbital characteristics. So it's like there are some projects, as far as I know, that are trying to address this the timing issue. And also there are some works that are trying to use LEO satellites with the predictable orbits, of course, for some sort of a GPS-like solution, GNSS solutions. But yeah, overall, if we want to make them coordinate with one another, we don't know how to synchronize them yet.
Would you say a little bit more about, you call them reflective intelligence surfaces? Can you say a little bit more about what that is?
Exactly, I would be happy to. Actually, these are, if we use metasurfaces as reflectors, then we can actually control the reflection error, so that we don't have to obey Snell's law of reflection when we are transmitting when we are reflecting from this surface. So if we have these metasurfaces with controllable phases, reflection phases, what we can do is we can try to use this kind of a reflection to generate multipaths that add constructively at the destination. So this is a way of like using, it's almost like using a mirror, and then we can change the initial angle of the mirror so that we can reflect the signal to the desired destination. So that seems promising in space communication scenarios, because there is no reflections. There's not much multipath around.
So this is free space optics. This is satellite to satellite or satellite to ground?
Could be in either way, and that the reflective. It's mostly studied in terrestrial networks as well. Like there are some suggestions to cover, for example, building surfaces with intelligent surfaces, so that we can avoid the urban corridors. But personally, I think from satellite to satellite, it has a very promising application.
So would that be multi-hop? You use one satellite as a reflective service so you can communicate from one place to another? Why not go directly? Why do you need to reflect off of one satellite to another?
Very good question. If there are so many of them, that was our starting point. If there are so many satellites and then each of them have their own purpose, and then if there's this additional surface that can be used to reflect the transmission, so that's why we came up with that kind of a construct. Well, we are still trying to publish it, so we are still trying to convince reviewers as so I see the validity of your points.
So I mean, if you did reflections, maybe you could use that as if every satellite was reflecting like a timing source. Maybe that's a way of doing synchronization.
Well, I have never seen anything like that. Yeah, could be.
Oh, okay. Could this also be used like a corner reflector will send you shine a light at something and it'll send it back to you? Would that be one way of making satellites less reflective to optical astronomy or radio astronomy, except that you might blind the satellites above you if you're reflecting all the light back out, maybe at the sun?
That is very true. So we have to think about it from all possible receptors around it. So there are all these risks associated with it. That is true.
So it would keep the satellite cool and maybe keep the skies dark, but or reduce the thermal load, solar load on the satellite, and still keep by reflecting the light back to the sun, and that would maybe make astronomy more possible.
Exactly. So there is a big like any kind of reflector that is put up in the sky is changing the radio astronomy measurements. So
Right.
yeah, that needs to be recalibrated based on that, as far as I understand.
Okay, because it's light pollution from cities on the Earth is a real problem for radio or optical astronomers now. Their light levels are above threshold where they wouldn't be built there today, I guess. It's a real problem.
Yeah. So I think SpaceX so far has been trying to address these problems with their own solutions. But overall, as space is getting congested, we should find a better solution for all this.
With the hold and forward. Oh, wait, excuse me. With the you said the hold and forward approach, the DT. What was it? Delay
tolerant networking.
How much memory is required for something like that?
That is also a very good question. Like how like it depends on how wide do we need to consider the routing tables. So if we should we do routing for the whole constellation or just the cluster of it? And if it's only for one cluster, do we change the elements of the cluster? So we are trying to look at these problems at the moment, and we don't have a clear solution at the presently.
So don't you need to buffer the data as well? It
Uh-huh,
seems like
yeah.
a lot of that seems like there'd be a lot of data. That seems like it would take a lot of memory with the high data rates that you want to push through them, right?
Exactly. And then given that this will be like a for let's say if you also need to provide some quality of service there, the problem gets even more complicated.
Yeah, these aren't going to be small satellites then, right? They're going to be pretty monstrous things, right?
Yeah. It's not only from the antenna perspective, but from the payload perspective as well,
Yeah,
for sure.
It's like putting a whole cloud in the sky, right? A whole network.
Yeah, exactly.
Put an AWS in and put it in orbit.
Yep, and based on it, I think IBM also has some solutions there, and then Microsoft is also considering some space data centers. So it's computational offloading in space is also yeah, that's we may see that in the future.
Yeah. Yeah, Google Cloud. Now it's Google Space, something like that. Yeah. Wow. Anybody else have questions? All right. I'm going to stop the recording.
Recording stopped.
Okay. Now, does anybody have questions that please feel free to ask questions without the recording going? Oh, sure. Live streamers, thank you so much for joining us tonight. We'll work with you to maybe stream more of our programs in the future.